So let's take a look at one like number 6. We have the integral of 9 over x cubed dx. So anytime you have a variable in the denominator, okay, except for x to the 1, we're going to rewrite this with a negative exponent. We have a property of exponents that says if x is in the numerator to a negative exponent, we can put it in the denominator with a positive exponent, or if x is in the denominator with a positive exponent, we can put it in the numerator with a negative exponent. So we're going to take advantage of this rule and move this to the numerator, x to the negative 3. Now remember, as long as x is not negative 1, we can use the rule. First of all, let's bring the 9 out, okay? And then we're going to add 1 to the exponent, x to the negative 3 plus 1. We're going to divide by negative 3 plus 1, and then we're going to add our constant. So we can reduce these. You can actually skip that step and say x to the negative 2 divided by negative 2 plus c. And we're not going to leave a negative exponent in our answer, so it's going to be negative 9 over 2x squared plus c. And we have to remember to put the plus c because at any constant, the derivative would have been a 0, and there's no way we can know what it would be. So just to recap, the first thing you do when you have a variable in a denominator, just a single variable monomial like this, is write it with a negative exponent as long as that's not a 1. Okay? You can't do it as a 1 because negative 3 plus 1 would be a 0 and you'd be dividing by 0. That's the one that's associated with the natural log. So just remember, as long as it's not a 1 in the denominator, you rewrite it with a negative exponent. I brought my constant outside, and then I use the exponent rule. Add 1 to the exponent, divide by that new exponent. So negative 3 plus 1 is negative 2. Divide by negative 2. That negative 2, I can put that negative in the numerator or out front. It probably will give me credit if I leave it in the denominator, but that's not good format. So let's enter this and check it. Negative 9 over 2x to the second plus c. And again, upper or lowercase c is fine. Number 7, the integral negative 15 t to the negative 3.5 subtract 3 t to the minus 1, all of that is dt, meaning the derivative has been taken and we're going backwards to the original function. Now I'm going to put these constants out front, and I'm going to remember, if I'm separating these terms, I need a dt for each one. Okay, can't take the integral without having the what we call the differential there, saying that a derivative has been taken. Now I'm just going to use the power rule here, but here I cannot use the power rule. It doesn't work when x is a negative 1, or when the exponent's a negative 1. So this is going to be negative 15 t to the negative 3.5 plus 1. That's the power rule. We add 1 and divide by the same exponent, 3.5 plus 1. Subtract 3, and the derivative of the natural log is 1 over t. So this is natural log, absolute value of t, and then plus c. So this is going to be negative 15 t to the negative 2.5 divided by negative 2.5, subtract 3, natural log, absolute value of t, plus c. And then I need to clean this up a little bit. Negative 15 divided by negative 2.5. A negative divided by negative is going to be a positive. 15 divided by 2.5 is going to be 6. So this is 6t to the negative 2.5. Subtract 3, natural log, absolute value of t, plus c. And in the best format, I wouldn't leave a negative exponent. I would move it to the denominator. That's a 2.5. So 6 over 2.5, subtract 3, natural log of t plus c. So let me say that again. 6 divided by t to the 2.5, subtract 3, natural log, absolute value of t plus c. 6 divided by t to the 2.5 minus 3, natural log, absolute value t plus c. Now, MyMathLab may allow you to leave this with the negative exponent, and if it does, you may leave it that way. But in the best format, it would be this. But I'm not going to count it wrong if MyMathLab doesn't count it wrong. Okay, number 8 has an e to the x in it. So let's review. If a function is e to the x, its derivative f prime of x is e to the x. That means if I take the integral of e to the x dx, my answer is e to the x plus c, because I'm going back to the original function, but I'm adding a constant just in case there was like a plus 2 or something on the end of that function. Now, if the original function was e to the k times x, where k is a number like 3x, right? The derivative of that is k times e to the x, e to the kx. So to get back from here to here, I got to get rid of this k. So the integral of e to the kx dx, it's going to be e to the kx divided by k plus c. And you'll see how this works when we do this one, okay? But remember, we're going to have, if it's got a number here, we're going to have to divide by that exponent, somewhat like we do with the exponent rule. All right, so let's try this one, okay? I've got the integral. I'll put my 6 out here because it's a constant. E to the negative 0.5x dx. So that's going to be 6 times e to the negative 0.5x divided by negative 0.5. Don't forget that number has to be divided there. And then plus c. So I have to do, I've got a 6 on the top here divided by negative 0.5. So I've got 6 divided by 0.5 as a negative is negative 12 e to the negative 0.5x plus c. Now I could write this negative 12 over e to the 0.5x plus c, but when our base is e with a negative exponent, it is okay to leave it that way. So MyMathLab should take it either way, and I will take it either way. So negative 12 divided by e to the 0.5x plus c. Okay, here we have 12x plus 5 quantity squared dx. So I'm going to let u equal 12x plus 5, and the derivative of u, but with respect to the x, is actually 12. So I take the derivative of that. Now I'm going to move this dx to this side, so du is 12 dx. So now I'm going to use some substitution in here. Okay, I'm going to put in things that I know. Okay, I know du is 12 dx, and I know u is 12x plus 5. So I'm going to say, okay, this guy is the integral of u to the second, because don't forget, u is 12x plus 5. And the problem is here I need a 12 dx, but I only have a dx. So here's what I do. I'm going to put in a 12 here, and I'm going to take out a 1/12 here. Because what's 1/12 times 12? Well, that's just 1. So look, so that I can have a 12 dx, I put a 1/12 out here. So I need a 1/12 here, and then I can write du. Because what is du? It is 12 dx. So if I put a 12 here, I got to take out a 12 here. Right? So now this integral is easy. That's 1/12 u to the third over 3 plus c. And that's 12 times 3 is 36. So keeping in mind what u is, that's 1 over 36, and now I'm going to put my u back in, 12x plus 5 to the third plus c. So I resubstituted, I simplified, and I put in the value for u. We'll have to do a couple of these. So 1 over 36, 12x plus 5 to the third plus c. Number 10. We've got the integral of 14 to the x dx. Now we looked over some rules in another video of what we do when this base is not an e. We know what to do with e to the x. It's e to the x. But remember, I'll bring up the rule so we can be reminded that when we have a base, this one right here, a base that's not a 1 and not an e, okay, so like a 2 or a 3, or like in this case we've got a 14, so this is for any base other than e and 1, then we have to take that base divided by the natural log of a plus c. Okay, now this is a positive 14, so we don't have to say absolute value when we do our log. It's 14 to the x divided by the natural log of 14 plus c. All right, look at this rule again. A to the x dx, the integral of that is the exponential expression divided by the natural log of the base. Again, no absolute value is needed because 14 is a positive number. So it's 14 to the x, all of that is over the natural log of 14 plus c.